physicsforme.com presents the concept of terminal velocity in the 5-minute video series which explains selected physics concepts in only 5 minutes. Terminal velocity is the term given to the limiting velocity reached by a body falling in fluid such as air or water. To help you understand the concept of terminal velocity and how it arises, we will make use of a couple of simulations which can also be thought of as virtual experiments. In this simulation, we have two identical balls that we will release at the same time in two different media, vacuum and air. First, we'll focus on how fast the two balls fall. Let us start the simulation now. Not surprisingly, the ball in air falls more slowly due to the effect of air resistance or drag. The black tick marks indicate the positions of the balls after successive intervals of 1 second. If we look at the ball falling in vacuum, we see that the tick marks become more widely spaced the further the ball falls. This means that the ball travels greater and greater distances in the same time. Hence, its speed is increasing as it falls. In other words, it accelerates due to gravity. If we now look at the tick marks in air, we find that the distance between them initially increases but eventually becomes constant. Hence, the ball in air eventually attains a constant velocity, the terminal velocity. Why does this happen? To understand why, we need to consider the forces acting on the balls, which are indicated by the force vectors on the ball. The green arrow is the weight of the ball and is constant, both in vacuum and in air. The red arrow is the opposing drag force, which is absent in vacuum, but in air its magnitude increases with the velocity. Let us reset and run the simulation again. This time we will focus now on how the drag force vector changes as the ball falls in air. Initially, there is no drag force because the ball is at rest. But as it accelerates downwards, the drag force vector increases. The more it increases, the less the resultant downward force is. By Newton's second law, F equals ma, the acceleration therefore decreases as it falls in air. This can also be seen from the acceleration time graph shown here in blue for the ball in air. Let us restart the simulation once more. As you can see, the drag force increases and eventually the upward drag force vector becomes equal to the downward weight, and so the resultant force on the ball is 0. By F equals ma, this means that the acceleration is 0. Hence, the ball has attained constant velocity, terminal velocity, as indicated by the blue curve in this velocity time graph. The second simulation shows an application of the concept of terminal velocity to a real-world example, that of a skydiver. A skydiver falling from a plane without a parachute eventually attains terminal velocity as indicated by the velocity time graph here. But unfortunately for him, that terminal velocity is rather too high for his safety. So let us give him a new life and a working parachute. Because of its large surface area, the parachute greatly increases the drag force, which reduces the terminal velocity to a much lower velocity, as shown on the graph here. Hence, the skydiver is able to make a safe landing. We hope you have found this video useful. For more videos and other free resources, please visit us at physicsforme.com.